Hello. I think probably I haven't gone into enough tech, but I'll see what I can do. So just to give you a bit of context, I'm kind of an old hand at open source. I started Collabora, started CodeThink, these guys over here. And I was around the really early days of open source when conferences were in like small lecture theatres from a random university in the middle of Europe, or or in a sports hall somewhere in Brazil, sleeping on the floor. And of course, I've been through this journey where nowadays it's very posh and there's all these things happen, and we spend lots of money going to conferences. And I miss the old days. And then a few years ago, I started looking at what was happening with all this open source starting to come to chip design. And I was like, that reminds me of the old days. It's like 2001 all over again. And in a lot of ways, it is like 2001, right? So out there's loads of stuff going on, and some of it's very, very good. But much like with open source software, back in those days, it was kind of low-hanging fruit that were being picked up, and also doing the things which people couldn't do, right? You think about the early cloud systems, right? All those happened because there was open source, there was Linux, and there was Python to build it out of, and you couldn't have done it with Microsoft. And so when we look at, few years, 3 years now, just under 3 years ago now, I started thinking, well, what's the business that can be built now with what's happening in open source semiconductors now? And that's what I'm going to talk about. So we've been kind of building that for a while. We got our first kind of pre-seed funding, as they call it, in April last year. And then we're about to raise another, which is about 1.2 million. We're about to raise another like 5 million in a couple of weeks. So we'll be opening that. And, it took a long time really figuring out, so what's the market? What's the problem we're solving? What's the thing that people need to do that the current ecosystem doesn't let them do, right? And the big trend that we came across, and the investors that invested in us have been coming across, is verticalization, right? So we all know how Apple and Google have been building their own silicon for solving their problems for their products. That's allowed them to reduce the cost, get better performance for their use cases, and have innovation that they wouldn't be able to have otherwise. But the problem is, and for anyone who's ever worked with the EDA tools, the electronic design tools, one, the tools are really expensive, but that's not actually the big problem. The big problem is actually how the hell do you build a team to build chips, right? That is actually the big problem, because there's no standard way of doing anything. Everyone's different. And so you've got to start off with hiring somebody who's built a team that knows how to build chips. So you find one of those and hire them. Then you've got to try and find all the people. They're very expensive. They're rose hen's teeth. In Europe, we're currently estimated to be 250, down by about 250,000 engineers who know how to build semiconductor tools. Build chips. If your market cap's only, $1 billion or $500 million, right? No chance. You can't do what those guys are doing. But they want to verticalize. You want to be able to control my supply chain, especially after all that nonsense that happened with COVID. I need to be able to control my supply chain. That burnt me very badly. I need to be able to innovate. I need to be able to be responsive to market changes. And I need to reduce BOM, and I need to reduce power usage. And so the standard, let's find some off-the-shelf parts and put them together to make a product, increasingly doesn't cut it. For cost reasons, for innovation reasons, and for security reasons, security of supply and security of your product. So that's what we see here, right? So we think, and we're seeing it, that there's a certain amount of people out there who already do custom chips that clearly the big guys, but also people go out and they hire design firms to do a custom thing for them. We're seeing that number massively increasing, and what that's eating into is the current off-the-shelf chips market, right? So, off-the-shelf chip market, 400-ish billion. We're kind of focusing really on the kind of more embedded side of that, right? We're not trying to go for NVIDIA or Intel or anything like that. We're really thinking about the people that make products. So we think there's probably 80, 100 billion sort of market there that we could take over. So that's the aim. But all of this is only possible. This is kind of what I was talking about. So companies, they've got the reduced competitive advantage. They have all these things that they need to make that they can't make, or they can't get the chips to make. Most of the innovation has to happen in software, right? You have to go and buy a microcontroller, and then you've got, and then we've got to do our software updates, and then we've got to coordinate this over the cloud and all these thousands of devices. And if anyone's ever worked with automotive, they're having an incredible time with that at the moment. You've got 1,000 chips in a car, which came from probably about 100 different suppliers who all have different development schedules for the software that they're writing. And that's kind of huge amounts of pain. So I can't react. It's costing me money. It's causing me pain. And it takes me longer to get to market because I've got to design the hardware first, and then I've got to write a whole load of software. And so what we're trying to do, really, is build a platform as a service, and we're building that out of open source. The whole thing's not entirely open source, but the main chunks of it are. So one of the reasons that this hasn't been possible before is that you'd have had to use the EDA tools, right? So that gives them a chokehold, and they cost, you can't cloud scale the place and route tool from Synopsys. It would bankrupt you, right? So it needs to be open source, and open source, the key thing about open source always is that it's a way that allows unrelated or even antagonistic players to work together successfully. And so what we're starting to get now is a few key open source projects that with the really hard bits of making chips, and people collaborating on those and pushing those forward, and gradually getting them to kind of commercial level in a domain at a time, right? And so we're integrating that together and building a platform where you can take some of your software engineers, maybe a few kind of like PCB level engineers, maybe you hire a few RTL engineers. You don't want too many, they're weird. And do a design, and then get that design built, right? Actually, get a chip out at the end, and then get a chip in volume out at the end. Because people talk a lot about the skills to do digital design or analog design, but that's actually only half the problem. The rest of the problem is then actually you've got to get the foundries to actually talk to you, or the foundry partners to talk to you. And seriously, as a startup, that's kind of nigh on impossible, right? We're very lucky that we've got a few kind of supporters in some of the big foundry services companies, and they're going, right, you guys, you're good, you get that organized, but it's still, that is not fun. Part of our funding last year came heavily from automotive, right? So they are really failing this. So if you think about an automotive manufacturer, even the biggest ones, say Toyota, sold about 10 million cars last year. 10 million chips, you don't really get very far making 10 million chips. At Global Foundries, I think the minimum order, and don't repeat me on this, something like 20 million worth of wafers, which is about, for a big chip, about 20 million chips, right? That's your minimum order. So we need ways that they can use your software team, and actually you can do hardware-software co-development to build your product, right? Or maybe you decide not to do any software at all. Like, get halfway down and you go, actually, let's just do all this in hardware as a state machine. It's easier and more secure. And part of how we do that is using one of the really great open source projects out there, which is called Amaranth, which is basically making hardware with Python, right? You write the Python that builds your hardware. I call it algorithmic hardware design sometimes. It can be you can do it very algorithmically, or you can do it very detailed oriented. There's a great CPU generator actually out of Poland that I've been following along and going, ooh, that's brilliant. And so you need that. You need to be able to pull together the kind of bits of IP, the interfaces that you need. So what we're going to do, and this is probably a bit of a longer term, in a year or so, actually have a marketplace out there. So there's so many companies in Europe and the UK that have built bits of IP, a memory controller, a USB interface, the analog SerDes, as it's called, for how you talk to your PCI or your phone camera. So they need to be able to be, you need those things when you're building a chip that's a real world chip. So we want to be able to get those people to be able to, to be able to get that stuff into the marketplace and be selling to the end users rather than what happens today when they have to sell to the big fabulous semiconductor vendors who obviously kind of go, yes, that's great, and then build their own. And if automotive, we need to be able to do automotive validation, right? We need to be able to go ASIL, ISO 262. So that's getting built into the platform. And at the end of it all, you need to be able to go, okay, and I'd like 500,000 of those or 10,000 of those, right? And that's where we want to end up. We want to be able to have even a small OEM that's selling 10,000 units a year to be able to go and have a custom chip in there. And that's going to save them money over what they're currently doing and give them that ability to innovate, which means next year there'll be 100,000, 500,000. So that's a bit of a kind of like the overall kind of context. I think it's kind of important because quite often in open source, we talk about the tech, but we don't think about what's the business case that's supporting this. And that's why some projects live and some projects die. So the three main components of the tech stack that we're building on. It's Amaranth, so I've talked about that a little bit, and I'll give a little bit of an example of that. Second key thing, and this has been like really transformative. I'll just wait for this person to stop talking. Cheers. Actually, and the thing that's actually been transformative and actually kicked off a whole host of projects in this space is a project called Yosis, done by a great woman called Claire out of Austria. And this is a synthesis tool. So for those who aren't used to the terminology in this space, this is the tool that takes your description of what the hardware is, your RTL, your Verilog, and then figures out how to actually make that with gates, right? That's what synthesis is. And that's been incredibly important. That's what's given us all the open source FPGA tool chains that I'm sure a lot of you have started to use. But that just gets us what the gates are, right? So the next thing is how do we take those gates and turn them into effectively what you need to send to the manufacturers, right? What you need to send to the foundries. And what that is basically some very high-res pictures, right? It's a set of layers of very, very high-res pictures saying, right, there's a little strip of N silicon here, and there's a strip of P silicon here, and here's a bit of strip of metal layer on that layer before you build this layer. And you end up with a stack of pictures. And that is actually the hardest bit. How do you get from gates to the description of what is actually being built on the silicon? What are you going to make your mask set out of, as they call it? And there's a couple of projects really we've been working on that. We're working with, so actually Coriolis is one of the lesser known ones. And it came out of the Sorbonne, the LIP6 group at the Sorbonne. Actually based on tools that, if anyone's old enough to remember, Boulle, the French supercomputer manufacturer. So in the, I guess the late 90s, they decided they weren't going to be making their own tools for making chips anymore. They said, okay, Sorbonne, do you want it? And Sorbonne said, oh, go on then. Oh, do you mind if we open source it? Do you mind if we make it GPL v3? And they did. Sorry, stop this phone. And so that's kind of the basis of that. So that is a great tool which has a full Python API for all the detail work you do. And we're using it to build about 130 nanometer designs at the moment. And we've got the path forward to how we go down to probably 22 nanometers on that. It gets a bit more fun when you go under 22 nanometers because of the shape of your transistors. And if anyone wants to hear about that, I'll tell you about it afterwards. And so we just founded a foundation for Coriolis, and that work's going well. So, and actually one of the big chunks of work that we did with Coriolis was it was very much hiding under a bushel. There was like it was on its own private GitLab server inside the Sorbonne, which you could get to, but if you wanted to commit, you had to send in, like an LDAP key so they could add you to the LDAP database. Was that a question? Sorry, no. And of course, there was no CI properly, and no contributor rules and no documentation. So that was a big chunk of work, actually, as well as doing the work to get it to support the target processes, the target manufacturing processes that we're working with. And so these are kind of the main bits. There's a whole lot of bits in between, lots of detail, but I'm not going to go into those. But I thought I'd just give you like a little taster of what the environment feels like, right? I wanted a video of our current environment, so I'd give you a really cutting-edge one. No one got back to me, so brr. But if you followed me on LinkedIn or Twitter, you'll see it as soon as that's available. But let's do it a really, really simple system-on-a-chip design, which is what I've drawn up here. So we want a nice kind of simple one cycle, one instruction per cycle CPU. We want a bus. We probably mostly use Wishbone. We're also doing AXI, but Wishbone's probably the most furthest on, which is the open source and open bus standard. So when you connect to a bus, you need an arbiter that is deciding is it an instruction that I'm fetching, is it data that I'm fetching from the CPU, and then we've got the bus. We want the memory on there, and then we probably want some peripherals. So in our system, there's a this is the equivalent of the AHI bus, I think, in ARM, for those who know that sort of stuff, but basically a peripheral bus. And I've got a serial port on there. So this is like world's most basic system on a chip. But still, if you were going to do this from scratch in standard tooling, probably a year, I guess, right? Assuming or maybe less if you already had all the tooling to generate all the bits. But if you're doing it seriously from scratch, yeah, good luck. And so I've extracted the main bit of what the code is for this. So you see it's Python. This is test code, so it's kind of a little bit more verbose than I do for kind of demo code. So we're going, okay, let's create ourselves a CPU. We want to have an instruction cache, and that's our size. Want some memory, so we need some ROM to boot from. So let's put a 4K ROM on there, and I'll tell you how that gets loaded afterwards. And we want a nice async serial peripheral, and then we're going to connect our async peripheral to a peripheral bus, and then we want to connect our peripheral bus to our Wishbone bus. Okay, so that was relatively straightforward, wasn't it? Let's see what happens in the rest of it. And then, of course, we need to connect the CPU to the Wishbone bus. So we'll need an instruction decoder, and we'll need an arbiter so we know whether we're fetching data or instructions. And then, so let's create our instruction bus, data bus, connect those up, connect up our ROM bus, and then add our... So this gets us our CPU connected to a Wishbone bus, and then we connect up our ROM, and we connect up our peripheral bus. And we're done. That's it. There's a little bit of gardening detail, I'd say, but that's the main bulk of how you do it. And then you can kind of run it through the tool, and like I was saying, you get a bunch of high-resolution pictures that you can then go send to the Foundry. And of course, with the version of ChipFlow that we'll be launching in probably autumn this year, you as an open source project will be able to put a project on there and then get a test chip made. Get it sent back to you, get 100 test chips back. Still figuring out what the cost's going to be and how much we can kind of lower that cost when you actually do the manufacturing, but to use the platform is going to be free. So that's what it ends up looking like. And that's pretty much the end of my talk. So I'll just take any questions.